All right, let me just share the whiteboard. Can you see the whiteboard? Is it visible to everyone?
Yes, sir.
Okay.
Yes, sir.
Let me just copy the question. Okay, so okay, is it visible? The question is visible to everyone?
Yes, sir.
Okay, so what is been given in the problem is an oil. Maybe I'll just start writing. Okay, so an oil with the thermal conductivity of 0.138 watt per meter degree Celsius flowing through a 25 mm radius pipe exchanges heat with an external medium. At a particular section of the pipe, the radial velocity and the temperature distribution in the oil are given as. So basically the velocity is given as this. V is given as 0.5 minus 800 R square. This is what the equation is given for V, isn't it? And temperature T is given as 60. Temperature is given as 60 plus 1.728 into 10 raised to power 5 R square minus 3.073 into 10 raised to power 6 R cube. Okay, this is what is been given here. Velocity is in meter per second, R is in meter, and in this equation temperature is given in degree Celsius. Okay, now what is the question one? Determine whether the oil is in laminar or in a turbulent flow. That is what we have to determine. Okay, now so in this case, let's say this is equation 1, this is equation number 2. If we look at equation number 1, equation from equation 1, we can represent this equation as, we can take this 0.5 common, 1 minus, this will be 1600 R square. Do you all agree? Yes or no?
Yes, sir.
Yes, sir.
Now this type of velocity profile, when we see this type of profile, when velocity is proportional to R square. Can you say anything on that? This will be in a laminar flow, isn't it? In a laminar flow, typical expression is this: V naught 1 minus R by capital R square, isn't it? This is what the equation you get. Yes or no? This is what the equation you get it in a laminar flow, isn't it? So if you compare this equation number 3 with this new equation number, let's say 4, so these are same, nearly the same, isn't it? Yes or no? So for instance, in this case, what is the diameter, what is the radius is given? 0.25, isn't it? So I can represent this as, I can represent this equation as V equals to 0.5, 1 minus R divided by, what is the radius? 0.25. So if I put that as 0.025 square, it is satisfying the equation, isn't it? Don't you think? What is 0.025 square? 0.025 square is 6.25 raised to the power 10 raised to power minus 4. And inverse of that, if you take the inverse of that, then you get 1600, isn't it? It's satisfying the equation. Yes or no?
Yes, sir.
Correct. So what we can say? What we can say from this velocity profile? This velocity profile is only for a laminar flow, isn't it?
Sir, if it wouldn't be of laminar flow, then we can say it is turbulent.
If it wouldn't have been in laminar flow, then in a turbulent flow, R raised to the power 1/7 or something is the exponent, isn't it? If you recall your transport phenomena in a turbulent flow, the velocity, the average velocity in the pipe is related to R raised to the power 1/7 or something. Isn't it? It's not square. So you will get a very different relationship in that case. But since this R square is there and which is satisfying all the values, isn't it? This is what the radius is. R. This is nothing but R, right? R is given as 25 mm in the problem, isn't it? So it is perfectly satisfying the equation. So clearly we can conclude that part A flow is laminar. Do you all agree or not?
Yes, sir.
Flow is laminar. Now the second question is oil being heated or cooled? What do you say? Whether the oil is being heated or cooled? Which one is true? So you can calculate what is the value of T at R equals to 0 and at R equals to R, capital R, isn't it? So if T at R equals to capital R is higher than at R equals to 0, clearly oil is being heated, isn't it? Yes or no? Or you can calculate what is dt by dr at R equals to R, isn't it? Do you all agree or not?
Yes, sir.
Yes, sir.
Yes, sir.
And if this comes out to be a positive number, clearly the oil is being heated, isn't it? So calculate dt by dr at R equals to R. What you are going to get? With this, you are going to get so okay, 1.7 1.728 into 10 raised to power 5 into 2 R, isn't it? Minus 3.073 into 10 raised to power 6 into 3 R square, and everything you are calculating at R equals to 0.025. So what is the value you are getting? What is the value you are expected to get here? Anybody? Anyone? Are you getting this value? Just check. 10 raised to power 3.
Yes, sir. I'm getting this value.
So, and this is definitely greater than 0, isn't it? That means what? Oil being heated, isn't it? Do you all
Yes.
agree?
Yes, sir.
What is part C in the question? Part C in the question is what? If you go back and see, part C is calculate the cup mixing temperature, or cup mixing temperature is nothing but the average temperature. This concept you will get to know in the next class tomorrow. Okay, so cup mixing temperature is the temperature which you average over all the variable values. So what are the all variable values? Velocity, density, specific heat, viscosity, and temperature. Everything you combine and then you calculate the average value. So cup mixing temperature is nothing but, I will write down the expression for that so that you will appreciate what I'm trying to say. So cup mixing temperature. No, point C is what? Okay, cup mixing temperature is point D. Calculate the average velocity of the oil. So what will be the average velocity of oil? So V naught we are interested to find, isn't it? So what will be the average velocity? Hello?
0.5.
It will be 0.5 meter per second. Now cup mixing temperature or bulk temperature, you call it bulk temperature. So this is the average temperature. This is nothing but the average temperature. Okay, average temperature averaged over all variables. Okay, so this is calculated as TCM is calculated. Cup mixing CM is for, sorry, cup mixing temperature is averaged over 0 to R. What are the different variables I am having? So I can have density changing, I can have specific heat changing, I can, okay, then again 2 pi R VDR into T and divided by 0 to R rho Cp 2 pi R VDR. Okay, so what this temperature actually, if you look at this particular expression, so what we are doing, we are, so see, between 0 to R, what are the different quantities which are changing? Different quantities, those are changing with respect to 0 to R is rho, Cp, R and velocity V, isn't it? These are changing and temperature also changing. So this is averaged over all these variables. Can you see? So this is something called as a cup mixing temperature. Is it clear?
Sir, this is the standard formula for calculating.
Yes. So here, in a way, what it is averaged over energy. See, 2 pi R VDR is basically what? This is nothing but the mass flow rate, isn't it? Velocity into this area, isn't it? This is a mass flow rate multiplied by, sorry, a volumetric flow rate multiplied by rho will give you a mass flow rate. Mass flow rate into Cp will be what? MCP is the nothing but the enthalpy you can carry, isn't it? Multiplied by temperature. So this is nothing but energy, total energy. And total energy averaged over 0 to R and divided by what you are doing, you are dividing by mass flow rate, average mass flow rate, isn't it? So basically you are getting the cup mixing temperature T directly here. Is it clear in a way?
Yes, sir.
Okay. So these two expressions we are going to see in the tomorrow's class. Okay, but I am writing it directly. Okay, so now in this case you can put all the values here. You can put all the values. So density is not changing in the given example. Density is not changing. At least we don't know how density is changing. So that we can consider as a constant. Specific heat also we can consider as a constant. But velocity we have already given the expression. So let us, do it in terms of velocity and temperatures. Okay. So in this case, what we are going to get? So this will be 0 to 0.025 0.5 1 minus 1600 r square, isn't it? R square. This will be the expression for velocity. Expression for temperature we can write again as 60 plus 1.728 into 10 raised to power 5 r square minus 3.72 into 10 power 6 r cube into r dr, isn't it? So this will be numerator. Denominator will be again 0 to 0.025 1 minus 0.5 1 minus 1600 r square r dr, isn't it? So this integral you have to solve. Can you solve it on your uh, calculator? This you can solve the integral directly on your calculator. So just solve this integral and see what you are getting. Anyone? Hello?
1 minute, sir.
So roughly you are expected to get this value. Check whether this value is correct or not. This is what you are expected to get. Is it clear? Yes, no. Are you all getting the same values? Is it clear? Yes. Is this value correct? Anyone? Hello? So is this value correct, everyone? So you can
Finish plugging.
you can do this numerical integration. You should able to get this value. Okay, let's move to the next point. So next point is we have to calculate the local wall heat flux, isn't it? So local wall heat flux. So local wall heat flux will be given by what? Local wall heat flux will be basically K dt by dr at R equals to capital R, isn't it? That is what going to be the local wall heat transfer heat flux, isn't it? So dt by dr we have already calculated. If you go back, dt by dr at R equals to R we have already calculated, and that value is this 2.88 into 10 raised to power 3, isn't it? Multiplied by thermal conductivity will give you a local wall heat flux, isn't it? So in this case, what we are going to get is thermal conductivity is again given in the problem. So 0.138 into 2.88 into 10 raised to power 3. So what you are going to get is 397.4 watt. Is it clear to everyone? Hello?
Yes, sir.
Now the next question is, the last part in this problem is to calculate the heat transfer coefficient. So you have to calculate the heat transfer coefficient. Heat transfer coefficient. Now what will be the heat transfer coefficient in this case? How we are going to calculate the heat transfer coefficient? Anyone?
So this flux divided by delta T.
Heat flux divided by
Delta T.
Delta T. Which delta T you are going to take?
From center to the wall.
Center to wall. Why center to wall?
Heat transfer coefficient inside the oil we have to find out, right?
So I am asking why the center to wall and why not bulk temperature to wall temperature?
Sir, we'll take bulk temperature only.
Bulk temperature we will take, or a center temperature we will take?
Sir, bulk.
Bulk temperature?
Yes, sir.
Or bulk temperature or a central temperature? How many of you are saying? Anyone? So we have to take a bulk temperature, and this cup mixing temperature is nothing but the bulk temperature itself, isn't it? So in this case, the heat flux Q will be given by what? Heat flux Q will be given by H delta T, isn't it? Correct? Yes or no? And H TW minus T cup mixing temperature you have to take. Yes or no? Do you all agree?
Yes, sir.
And what is the value of Q we have obtained? We have obtained 397.4. Heat transfer coefficient is unknown. TW we can directly obtain. So TW you can obtain by putting R equals to 0 in the earlier equation. You can put R equals to 0. Sorry, R equals to capital R you can put here. So TW you can directly get TW will be what? 60 plus 1.728 into 10 raised to power 5 into 0.025 square minus 3.073 into 10 raised to power 6 into 0.025 cube. So what is the value? Anyone?
120 degrees centigrade.
So around 120 degrees Celsius you should get, correct. So now we can put that 120 degrees Celsius value here, isn't it? So what we are going to get is 120 minus cup mixing temperature. What we have obtained is 85 point. Is this value correct? 85.028. Anyone got this value? Is it correct or some problem is there? Hello? Is this value correct? Anyone got this value?
So we are plugging in the values and sir, I had a doubt that why are we using cup mixing? Like why are we doing bulk minus? I
So
didn't get
cup
that.
mixing temperature is what? Cup mixing temperature is the average temperature you are going to find out in a fluid, isn't it?
Inside the fluid.
Inside the fluid, correct. So that's why you are averaging it over the radius, over the velocity, over the all properties, isn't it?
Okay. So the flux would, okay, fine. So sir, this 120 degree Celsius, is it the temperature of outside the wall or just oil?
This will be a wall temperature. No? This 120 will be wall temperature, because if you are putting R equals to capital R, that is the temperature corresponding to what? Wall, isn't it?
Temperature
Temperature of the wall will be right, isn't it? Yes or no? This is okay. This is the pipe. This is the pipe. This is the R you are increasing, isn't it? And here it is R. So when R equals to R, this will be TW, na? Yes or no?
it's wall.
What? Is it not clear? Hello? Not clear? Please say it explicitly if it is not clear.
So maybe doubt would be that inside the the oil's outermost layer and the wall's temperature that might not be same.
No, not at all, not at all. I understood. Maybe that is what the question is. No. So see how temperature will vary. Okay. How maybe I just plot roughly a temperature profile. If I plot, maybe I will have a temperature profile something like this. Just a minute. Maybe my temperature profile, let's say this is R is increasing, isn't it? So my temperature profile, and let's say this value is capital R. So my temp, and this is 0. So my temperature profile is something going something like this, isn't it? This is R at R. Maybe even though this is a film, but doesn't matter, isn't it? This temperature is still at R equals to R, isn't it? Yes or no? Maybe a more better representation will be this. Okay, I'll just do it. More realistic representation will be this. From 0 to R, your temperature will be something like this, and then here the film is there. Okay, but this temperature anyway is at R equals to R, na?
Yes, sir.
Okay, and this entire thing, including this film here, this we have already accounted. Is it clear?
Internal film in the oil.
This we have already accounted. So anyway, in this case, what we are going to get? We are going to get this. So H is calculated as 397.4 divided by 120 minus 85.028. So what is the value? My doubt is whether this value is correct. Anyone can confirm? Anyone can confirm whether this value is correct?
So I was doing it on the mobile, so I'm just trying, plugging in the values. I don't have a scientific calculation.
Acha. So hopefully it should be correct. 397.4 divided by 120 minus 85.028. So this comes out to be, H will come out to be 11.3633 watt per meter square degree Celsius. Correct? And Nusselt number will be given as, by HD by K So we will have 11.3633 into 2 into 0.025. So that will be D divided by thermal conductivity is 0.138. So this comes out to be 0.025 divided by 0.138. So this comes around 4.117. Check whether this is correct or not. Is it correct? Is it correct?
Yes, sir. Value of Nusselt number is correct.
Okay, so this is the solution. Can we move to the next problem? If it is okay to everyone. Can we move to the next problem? Next problem will also be a little bit time consuming.
Yes, sir, we can.
Acha. Okay, so the next problem again, let me just copy the problem statement. So some of these correlations we have not done, but hopefully in the next class. So tomorrow we have a class, isn't it? So we will cover these correlations tomorrow, but I will be using this correlation directly today. So please bear with me. What happened? Okay, so second problem is interesting. So there is a double pipe heat exchanger is there. Okay, I will just draw it again for your understanding. So there is a double pipe heat exchanger is there. Okay, so this is the double pipe heat exchanger. What is been given is mercury purified by distillation is cooled by passing it through a double pipe heat exchanger inner tube. So okay, so this diameter, this inner tube diameter is given as 13.5 mm. Okay, this is what is given, and what is going in. Maybe I'll just show this by a different color so that we are not confused. Okay, so the mercury. Okay, so mercury is going here, isn't it? Mercury. This diameter is 13.5 mm. Okay, again what is given is outer diameter of this inner pipe. Outer pipe is 41 mm. So this diameter is 41 mm. Okay, again the wall thickness, this wall thickness here is given as, wall thickness of the inner pipe is given as 2.75 mm. This is given. Okay, mercury is entering at the rate 1500 kg per hour, and temperature, let's say T1 is 250 degrees Celsius. Here T2 is 40 degrees Celsius, isn't it? Correct. Again the water is entering here. Cooling water enters at the pipe at 26 degrees Celsius. So here let's say, So this is TC1 and this is TC2. Hot fluid is mercury, na? So this will be TH1 and this will be TH2. TC1 here will be temperature is entering at 40 degrees Celsius. Okay. Just a minute. Cooling water enters at 26 degrees Celsius. So 26 degrees Celsius and leaving at TC2 at 40 degrees Celsius. Okay. Another interesting thing is you may ask me why this, TC1 is entering at this end and why not at this end and leaving here. That if we are entering TC1 at this end and leaving here, that will not be feasible because then it will be a co-current flow, and in co-current flow the same temperature gradient cannot be achieved. Anyway, this thing we are going to look at in more detail in subsequent classes. So only possible contacting scheme we can have is like this, where TC1 26 degrees Celsius temperature here, this will be at this end where the temperature here is 40 degrees Celsius here. Okay, so that some temperature gradient is present between these two. Also here this outgoing of the cooled water will be somewhere here. Okay, we will not be able to have this if I, let's say, do this direction. Let's say if I include the water like this and outlet like this, I cannot have. Is it clear to everyone? If I represent my system like this with this entering here and leaving here, that I cannot have, because in that case what it will be, this temperature will be 26 and this temperature will be 40. So temperature here will be 40 and this outgoing temperature here also it will be 40. So is it possible to achieve the same outgoing temperature and the outgoing temperature for both the fluid? No, it is not possible, isn't it? So that's why this possibility is not there. This possibility is not there. Okay.
So the outlet temperature of water is not in our hand, right? It will be depending on how much heat.
But this outlet temperature here, let's say if I take the reverse way here, 40 degrees Celsius. So this, remember, from 26 to 40 it is increased, isn't it? Is it possible physically to have a temperature same as the hot fluid? There will be some resistance offered by this tube here.
Yes,
isn't
sir.
it? It cannot be, isn't it? So that's why that contacting is not possible. Only possible contacting is this. So that means if we start in a other way around, that is something called as a co-current flow, because the flow of the water and flow of the mercury will be in the same direction. But now the flow of the water and flow of the mercury is in opposite direction. Remember, here water is flowing in this direction. Water is flowing in this direction, whereas mercury is flowing in this direction. So it is co-current flow. But let's say if I include here and take my water out here, in that case, both water and the mercury will be flowing in the same direction. Isn't it? That is something called as a co-current. So co-current contacting is not possible in this case, even though in the problem it is not been given, but just by looking at these temperatures, I can clearly say that only the counter current contacting is possible. Do you all agree? You all agree with me?
Yes, sir.
Sir, could you repeat that?
Here I have taken this TC1, water is entering in the opposite direction that of mercury, isn't it? That I have selected because only in that case my temperatures are satisfying. So even if this cold fluid is entering here at 26 degrees Celsius, there is a temperature difference between this hot fluid and cold fluid. So clearly this is a feasible situation. But let's say if I have a other way around, if my water is entering from this particular end and coming out at this end, so here the temperature will be 26 degrees Celsius, whereas the outgoing temperature here will be 40 degrees Celsius. So this outgoing temperature of water and outgoing temperature of mercury both will be same as 40 degrees Celsius. Can I have such type of situation? Can I have a such type of situation where the cold fluid will be heated to a same temperature as that of a hot fluid? It cannot, because there is a resistance to heat transfer here in between. It cannot be 40 degrees Celsius, isn't it? It will be less than 40 always in that case. But my temperature are already given 40. That means the only contacting pattern I can have is a counter current contacting. I cannot have a co-current contacting here. Yes? Is it clear?
Yes, sir.
Okay. So let us try to do it quickly. Let us try to solve this problem quickly. Okay. So these temperatures are given. Again, what is been given is properties of the mercury and properties of water are given. Okay. 33 degrees Celsius. Because if you take the average here 40 plus 26, you will get around 33. That's why the properties of the water are given as the average temperature. Okay. All right. So you can say that both the properties here are given at the average temperature. All right. Okay. Now in this case, so there are three things happening. One is the heat transfer between the fluid here. Let's say this is location 1. This is, let's say, location 1, and this is, let's say, location 2. So whatever the temperature I am having at location 1 and location 2, what is the heat transfer between these 2 points that I can directly get by looking at the sensible heat of this mercury? Yes or no? So how much temperature of mercury is increased while traveling from location 1 to 2 that I can get, isn't it? And that will be given as MCPDT. Do you all agree?
Yes, sir.
Similarly, I can look at the water flowing from this end 2 to 1, and again I can calculate how much amount of heat is gained by the water from 26 degree to 40 degrees Celsius by calculating again MCPDT, but in this case MC CPC delta T, isn't it? Where MC is nothing but the mass of the coolant, CPC is the specific heat of the coolant, and delta T will be the change in the temperature of the coolant, isn't it? So these are the two factors, and these two should be same. And in addition to that, again I can calculate how much heat is transferred between this cold fluid and the hot fluid here across this surface, across this entire surface, isn't it? That will be given by what? That will be given by UA delta T LMTD. Yes or no? Yes or no?
So could you repeat the last line? UA?
Okay, so what I'm trying to say is there are three heat transfer you can calculate using three ways. One is the how much sensible heat lost by the hot fluid as you are moving along this direction, right hand side to left, isn't it? Correct? How much the heat is lost by the hot fluid. So that will be given by MHCPH delta T, isn't it? So in this case, delta T will be what? 250 minus 40. MH will be the mass flow rate of the hot fluid. CPH will be the mass flow rate of the. Okay, so I am writing these three factors. Okay, then it will. So first factor will be MH CPH
Delta T.
TH1 minus TH2. This will be one factor. Second factor will be MC CPC TC2 minus TC1. Yes or no? And the third factor will be UA delta T LMTD. And all three are going to give you what? All three will going to give you Q only. Do you all agree? How much
Yes,
amount
sir.
of heat lost by the hot fluid is the same as the amount of heat gained by the cold fluid. This is the amount of heat lost by the hot fluid, isn't it? This is the amount gained by the cold fluid. And this is nothing but the amount of heat transferred between these two. All three are going to give me same as Q.
Yes, sir.
Yes or no?
Yes, sir.
Yes,
Okay.
sir.
So now with this concept, we can solve this problem. We can solve this problem like, okay. So now in this case, cross-sectional area of the inner tube. Cross-sectional area of inner tube that we can calculate. Similarly, we can calculate the cross-sectional area of annular tube. Okay, both these things we can calculate, isn't it? And then we can calculate the Reynolds number. Anyway, maybe we can continue this in the next tutorial class, because anyway this is with respect to whatever we are going to cover in the next class. So let's not cover this part further. We will stop here, but we will continue this problem in the next tutorial also. Is it okay?
So
Because
what would be-
anyway some correlations I'm going to use here, and that we have not covered it. So maybe we should cover the correlations first, and then we will look at this particular problem in the next tutorial.
the next tutorial will be next week, right?
Next week, yes, next week.
We'll have
So
minor
when is your minor?
14 to 17.
14 to 17. So let me just check. 14 to 70. So we will not be able to have the tutorial. That's what you are saying next week?
Yes, sir.
So we can have the tutorial then on next week on 23rd. All right. But meanwhile, you try to solve this problem. OK, we are going to cover some correlations in tomorrow's class. You please try to solve this problem using those correlations. But anyway, we will revisit this tutorial again after your quiz is done, after your minor is done. Is it OK?
Sir, what
Okay.
is the syllabus of minor including these tutorials?
Whatever we will cover till tomorrow. Whatever we will cover till tomorrow. That will be the syllabus.
So Tut 5 would be covered, right? Like the concept.
This tutorial will also come.
So anyway, one problem we have anyway solved, and I have already given you some background, but this part we are going to cover tomorrow. So you can consider that this everything is there. OK, but anyway, this tutorial we will revisit again this problem in the next tutorial class. If you want me, I can cover this, but some of the correlations we have not covered so far.
Sir, I had a doubt. Sir, could you please explain why we used the bulk temperature in the previous question again when we were calculating the heat transfer coefficient?
Yes, we will go. This you are saying?
Yes, sir.
So what is the heat flux? How you are going to calculate the heat flux? What will be the heat flux? Q will be given by what? When we are taking H delta T, what this delta T basically gives? It's a wall temperature minus bulk temperature, isn't it?
Yeah, sir, but मतलब हम central temperature यहाँ पे क्यों नहीं लेता है?
No. So see, why we should take the center temperature? Center temperature, we can take the center temperature if we assume that the entire flow is stagnant.
Okay.
Isn't it? Then we should take a center temperature. But in this case, the flow is not stagnant.
Yeah.
It's a laminar flow is there, so we have to take this temperature should be a bulk temperature. Okay.
Yeah.
So in fact, one such derivation we will look at in the next class, where we are going to derive the expression for the heat transfer coefficient in the laminar flow. There also you will see that we will be taking a bulk temperature while calculating this Q.
Okay.
Okay.
Yes, sir. Thank you, sir.
Is it clear to everyone?
Yes, sir.
Yes.
I have a point 5 mm sort of thing. Like if I want to find the heat outside the tube, temperature outside this tube, can I use the same H for that? Because the Q will be same.
Please repeat the question. What is the question?
This H, I mean, is this H, will it work if I have to find for outside the tube temperature?
Where is the outside this temperature? Here you are saying outside. So in that case, you have to take the ambient temperature, TW minus ambient temperature. If you are looking at, okay, if you are, so see, if we are looking at the heat transfer between this wall, if you are taking, let's say, the heat transfer between this wall and ambient, then you will take this as TA and this you will take TW. Yes or no? Not clear?
So, but for that, the heat transfer coefficient would be different, right?
But then this heat transfer coefficient will be called as H0. In that case, this will be H0, and this is nothing but HI, isn't it? This we are calculating here as HI.
Sir, पर जब हम इस केस में करेंगे तो हम लोग outer layer of the wall करेंगे, है ना? मतलब जब हम TW लेंगे वो outer most.
Correct, yes.
Whereas इस केस में हम inner wall का ले रहे हैं, मतलब
inner wall में ही कर रहे हैं, yes. And we are assuming that the temperature of the wall here inside and outside both will be same, because this wall is made up of what? Metal.
Okay.
Isn't it?
Yes.
But in that case, if you are assuming both these resistances to be present, in that case, this H will not be there. Then in that case, what you will have? If you are including this resistance here and the resistance here both, then instead of H, you will have a U, isn't it?
Yes.
And 1 by U will be given as 1 by HI, 1 by H0 plus conduction term will also be there if the conduction resistance is present. If not, and this also you can derive based on either a outer surface temperature or inner surface. If you are defining it in terms of outer surface temperature, in that case, it will be R0 by Ri. Do you agree or not? R0 by Ri into 1 by Hi plus 1 upon H0.
Yes.
That's what you are going to get if you are considering both the resistances here. But this is not been asked in the problem. We are only concentrating inside the pipe. That's why we have used only H and not Hi or H0. Is it clear? Hello?
Yes, sir.
Yes, sir.
So is there any, so Achintya, you had some question.
Yes, sir. Sir, I have a doubt from previous lecture, sir. So like you said that in a metal that thermal conductivity is negligible, so we take the concept of lumped heat capacity.
No, in metals we are not assuming the thermal conductivity negligible. We are saying in metals thermal conductivity is very high. So resistance
Yes.
by
The
that,
thermal resistance is negligible, and so we take the whole temperature of the body, and when we calculate the change in unsteady state temperature, then we apply the lumped heat capacity concept and calculate the formula. Sir, I was saying that if we consider the gradient, temperature gradient inside the metal, and so can we apply this equation, unsteady state conduction in a sphere?
Yes, you can, but then you have to solve that generalized. Then you have to solve that generalized expression which we have derived.
Yes, just this unsteady state conduction in a sphere. If we take that gradient and consider that thermal conductivity is not, thermal resistance is not negligible.
Yes, you can, but then you have to solve the generalized expression. Remember, generalized expression also we have derived.
1 by alpha dt by dou d by dou d is equal to dou square.
That equation you have to solve, correct. So you have to solve the generalized expression which accounts everything. So maybe I'll just show you again one more time. Just a minute. Let me open the slide. So if you are trying to solve that, if you are assuming that everything is there, then you will have to solve this expression. So this is only the conduction expression, but in addition to this, you will have some convection terms will also coming into this mass heat balance. Okay. Is it clear?
Yes, sir.
Okay, so that entire thing you have to solve. So you will have similar term, but also in addition to this, some convection terms will be coming into the picture.
And sir, the expression like when we thermal resistance is negligible, so we derive this expression by losing lumped heat capacity Tt minus T infinity upon T naught minus T infinity exponential Biot number into minus Biot number into Fourier number. Sir,
Yes,
this
so
expression,
yes, so here lumped heat
yes.
capacity.
This expression we can apply only when Biot number is less than 0.1.
Yes, 0.1. Yes, very less. हेलो सर, मैं कॉल कर रहा हूँ आपको, बस गिव मी 2 minutes. ओके, अभी कॉल कर रहा हूँ आपको.
Excuse me, sir.
हाँ, please go ahead.
I also want to ask something from tutorial 4.
Please ask.
Sir, in the first question of the tutorial 4, you said ki while you were calculating this U naught, you said ki we could basically neglect the contribution of HI. But if you wanna solve this with the first principle, like the way you did it solve in the lectures, so the value of U naught that you're actually getting is 3 point something. And why
just a minute. Let me go back to the tutorial which you are referring to. Maybe I'll just.
Sir, can you please allow me to share this my screen? I think
yes,
I could explain better in that way.
Just a minute. I will do it. Just a minute. Tutorial. You are saying tutorial 4 or
Yes,
3?
4.
Okay.
Question number 1.
This is what the tutorial 4 is it?
Your screen is froze, I think. I'm not really sure.
I will reshare again. Just a minute. Is this the question?
Yes, sir.
This is the question you are saying?
Yes, sir. Yes, sir. Exactly this one.
So what is the question now?
You'll scroll down. Yeah. And you said ki HI will be very high. So you said ki the contribution of R naught by Ri into HI, that would be like very high. So when you add it to it will get neglected. But actually it's not getting neglected.
Okay. What I said is, okay. So here your question is why we have not included the terms corresponding to HI, isn't it? That's what you're saying?
Yes, sir. Like kind of this, but can you please allow me to share my screen? I think I can explain better.
What is your name?
Farman, sir. FARMAN.
Okay, just a minute. Okay, now you can present. I have allowed you to share.
Yes, sir. So is my screen visible now?
Yes, it is visible.
So while you were calculating this, so we calculate Q with the wall with the and both the fluids, right? And you said ki here you said ki the thermal conductivity of them is varying with a factor of 10 or more than 10, right? But in the question that you have given us, ki the thermal conductivity is varying first of all with a factor of 4. And the second thing, if you see if you calculate this using this, and you'll use this exact formula, Q is equal to T I minus T naught in this thing. So the value of this 1 over unit you get is the
no. Okay. I understood the question. What is the value of HI? Just tell me. What will be the value of HI here?
1 over 20, I think.
Why 1 over 20?
So because I think it's the heat transfer coefficient between this bulk and
No. Here, okay, this 20 is nothing but outer transfer coefficient. It's not the same. Okay, I understood the question. What maybe some confusion is there. Just wait. Okay. Can you unshare? I will go back to the same tutorial.
Yes, sir.
Okay. I think some confusion is there in understanding the. Okay, so now what is H0 and what is H0B? These both are the outer heat transfer coefficient here, not inside. And what we have neglected is the inside heat transfer coefficient. Did you get the point?
Okay, sir. So what is this HOB, which is 20 watt per meter square?
H0B is nothing but the heat transfer coefficient when I am having heat transfer coefficient outside here, when I am having this insulator around.
Okay, sir.
And when I am not having the insulator around, then I am having only 5 watt per meter square degree Celsius. Both are outside heat transfer coefficient.
Okay, sir.
HI is not been given here. What we are assuming that the velocity inside this pipe is very high, and because of that HI will be very high. That is not been given. That's why it is not been given. Okay. So the contribution of HI, that is why we have not included here. We are assuming that the heat transfer coefficient inside the pipe will be very high. That's why I have written HI will be very high.
Okay, sir.
Okay. So don't get confused with H0 and H0B. H0 and H0B both are the heat transfer coefficient outside. In one case there is no resistance, there is no insulation. In another case there is insulation. That's it. But both are with respect to outside.
Okay, sir.
In fact, when we are see, when we are having the insulator, in that case 1 by H0 plus this insulation resistance we have included, that is going to give me U0. But where I have used H0B I have used when I have used the bare pipe. Remember?
Okay, yeah.
Isn't it? So in this case, I have when I do not have any insulator, in that case only H0B will be there. Ideally, I should have H0B and the effect of HI included. But since HI is very high, I will say that the H0B will be the most appropriate one, because that is what the resistance will be present, isn't it?
Yes, sir.
That's why we have calculated just H0B AB delta T as a temperature, as a heat exchanged.
Okay, so understood.
So this is the heat exchange when I am using a bare pipe, whereas this U0, A0, delta T, this is the heat exchange when I am using the insulated pipe. Is it clear?
Yes, sir.
And the difference between that will be the amount of saving in heat loss.
Yes, sir, that's clear.
Okay. So don't get confused with this. H0B is not the inside heat transfer coefficient. No, not at all. This is the heat transfer coefficient of the bare pipe, and H0 and H0, just the H0 is nothing but the heat transfer coefficient when there is no insulator. Sorry, with insulator. H0 is the heat. Maybe I'll just write heat transfer coefficient
with the pipe and one is without the pipe. Yes, sir.
outside with insulator.
Yes, sir.
With insulator. This is what H0, and H0B outside heat transfer coefficient. Heat transfer coefficient without insulator. Is it clear? Now both are outside. Is it clear? Hello?
Yes, sir. It's clear.
Okay, so can we stop here? Is there any question?
Sir, I wanted just one last question, sir. If the Biot number is not less than 0.1, then we can't apply that equation.
Yes,
T0.
yes. Then
So in that case, we have to use the generalized heat transfer for sphere.
Correct. Yes.
Okay.
Okay, guys, let's stop here and see you tomorrow. Okay.